Today we want to talk about some of the weird effects of refraction. So a reminder that refraction happens whenever light changes from one material to another with a different index of refraction. The light speeds up or slows down, and as we already saw, that causes it to change direction. We had an equation developed by Snell, which allowed us to predict the refracted angle. We're not going to be talking about any math today. We just want to talk about some general ideas. Okay, so the first thing I'd like you to know, and you can write this question in your notes, is how is it that we see an object if the object is transparent? We would think that a transparent object should be invisible. So when we look at something that's transparent, like this giant vase, we know it's made of glass. We know the glass is see-through, and it's filled with water, which is also transparent and see-through. And yet, somehow, we can see it. And hopefully you realize when you're looking at this, the reason why you can see it is because the light that is passing through the glass and the water is going to be distorted. And because it's distorted, we can tell that there's something there distorting the light. You can see how the windows in the back of my classroom become much shorter, and that is not tall, but less wide. And you can also see how they flip direction. All right, so we can definitely see that there is something there distorting the light. If we have a flat piece of glass, there's not a lot of distortion when the light passes through it. And yet we can still see the piece of glass. This time it's not caused by refraction, but it's caused by reflection. We can see reflections in that piece of glass, and that lets us know that that piece of glass is present. So objects that are transparent are noticeable because of the reflection and the refraction of light. If we could somehow get it so that the object is submersed in a material that has the same index of refraction, it would become invisible, because at that point it would no longer be reflecting or refracting light. So if you look at this Pyrex stirring rod, you can see how it disappears inside this layer. This layer is a layer of mineral oil, which happens to have the same refractive index. Down the bottom, where it's in water, you can see the rod again because the rod has a different index of refraction. We can do this with a Pyrex test tube in a thing of mineral oil, and you can clearly see the test tube because the test tube is filled with air, which has a different refractive index. When we fill the test tube with mineral oil, it seems like the test tube disappears. And that happens because, again, there is very little reflection or refraction as it goes from mineral oil into Pyrex, back into mineral oil. Okay, the next thing we want to talk about are mirages, and you can see the mirage above the roadway. This is something you've seen before. The blue is the sky, the white is from the car, the green is from the mile marker. So somehow it looks like we're getting reflection off of the roadway, and that reflection we interpret as water. It turns out that's a bad assumption. It turns out it's not a reflection at all. So the clue to what makes this work is the fact that we tend to see these above hot surfaces. The other thing we see above hot surfaces is we notice that the light that's passing through the hot air gets distorted. And it's because air has different indices of refraction at different temperatures. In fact, it's not just temperature, it's temperature, pressure, and relative humidity all come together to affect the index of refraction for air. And it's these changing indices of refraction that lead us to see these mirages. So if we were to draw this out, we would have light traveling directly to our eye, and as long as the index of refraction remained the same for that entire journey, it would travel straight to our eye. We would have that light enter our eye and we would say, aha, we see a tree. However, there is also a ray of light that heads toward the ground. And as it heads toward the ground, it encounters air at different temperatures. This causes the light to change its path, to refract, to bend. And it can bend in such a way that it bends back up toward our eye. When we trace this backwards in our brain, it leads us to believe that there is a tree down here. And that tree that appears to be upside down looks just like reflection off of a puddle of water. It turns out it's not reflection, it's refraction. And it's refraction as the light goes from one temperature air to another. Okay, you can see this really well in this picture. It looks like we're seeing reflection, when in reality we are seeing refraction. We can actually have this happen in the reverse direction if we have cold air down low and hot air up high. This is an inverted system, so it's an inverted mirage, and it's sometimes called the Fata Morgana from Italy. You can see this really well with this boat. You can see how the light heading up into the higher level refracted back down again and makes us feel like there is a boat upside down above the original boat. Okay, so these are some of the tricks that can be played on us by refraction.